All right, this is 2-6, day 3. We're going to talk about slant asymptotes today. And there's another part to the day 3, the applications, which will be on a separate video. So this one is going to be all about how can I have a type of asymptote called a slant asymptote. And then the real life applications, again, will be in a separate video for day 3. All right, so when do we have a slant asymptote for a rational function? So when's the situation that that would happen? Well, it's whenever the degree of the numerator is exactly 1 degree greater than the denominator. So like say you have a degree 5 over a degree 4 or a degree 3 over a degree 2. That's when you're going to have these slant asymptotes. They don't have horizontal, because remember when you compare your degrees, if the degree in the numerator is bigger, it never has a horizontal. But what it could have is a slant in this very special kind of situation. So again, the degree in the top has to be exactly 1 more than what it is in the denominator. All right, well, how do you find them? How do you find those equations of the slant asymptote? You divide the numerator by the denominator. You actually just do the ratio. So it's a rational function. It's a ratio. So we're just going to divide the top by the bottom. And remember, to divide, we can either use long division or we can use synthetic. So we're going to have to decide what makes the most sense for us to do. But to do that division, we either are going to divide by long division or synthetic division. So remember, you can only use synthetic when that's a linear factor on the bottom. So hopefully we'll have some of those. But if it's long division, we're just totally fine. We know how to do that as well. But we're going to see what that slant asymptote gets closer and closer to. So let's take a peek at an example. So take a look at these two. Based on that definition, which of these, if either one, would have a slant asymptote, and how do you know? So take a moment, think about which one of those would. So compare your degrees. For the first one, we have a degree 3 on the top, degree 2 on the bottom. For this one, we have a degree 3 on the top and a degree 1 on the bottom. Okay, so which one would have a slant asymptote? Well, it has to be letter A, because that's where the 1 is exactly 1 larger degree in the numerator than it is in the denominator. So that's going to be your slant asymptote scenario. So that's definitely the one that's going to have one. The letter B doesn't, because it's 2 greater. So that wouldn't have a horizontal, because the degree is bigger in the top. It doesn't have a slant either, because it's 2 greater, not exactly 1. All right, so how do we find the slant asymptote? How do we actually calculate it? We divide. We do the actual ratio. We divide the top by the bottom and see what this function gets closer and closer to. What is that y value going to be equal to? So we unfortunately have to do long division, because look what we're dividing by. It's degree 2, so I can't use synthetic. So let's just be careful when I do this long division. So we're going to take x squared minus 1, and we're going to divide it. Now, or x cubed, I should say, minus 1. Now be careful. Remember, we have to have every place value represented. So what would have to come after the x cubed? A 0x squared, a 0x, and then your minus 1. So just be really cautious. You have to make sure that you have every place value represented. Now our divisor is totally fine. We have every place value there. Okay, so let's run through how we do long division again. So remember, we're looking at the x squared. What do I multiply it by to get an x cubed? Well, x squared times x would be x cubed. Remember, the other way to think of it is just see how many x squareds divide into x cubed. Just do the division. So take that term you're trying to make divided by x squared, and that's going to give you the exact same thing. Now, where would I put that x? Well, above the same place value, so above that 0x. Now we multiply x times all of those terms, so that would be x cubed. X times 3x would be plus 3x squared, and then x times 5 would be plus 5x. All right, and then what do we do with those two? Subtract. The first one should be 0 always. We're trying to divide in there evenly, so that makes sense. 0 minus 3 would be negative 3x squared, and then 0 minus 5 would be minus 5x. So we subtract. After we subtract, we bring down that next term and we start it all over again. And we have to think, okay, x squared times what will give us a negative 3x squared? So what would I multiply by there? So x squared times negative 3 will give you negative 3x squared. Or remember, our alternate way to think of this, take what you're trying to make and see how many x squareds divide in there and just reduce that fraction. That would reduce down to a negative 3. So we need a negative 3 up here, so a minus 3. And then again, we're going to multiply. So negative 3 times that entire trinomial there. So negative 3x squared. And then that would be negative 3 times 3 would be minus 9x, and then negative 3 times 5 would be a minus 15. All right, and then we're going to go ahead and subtract. Now, when we do this, again, this first one should be 0. So negative 3 minus a negative, yep, that's 0. Negative 5 minus a negative 9 plus positives, that would be 4x, and then negative 1 minus a negative 15, so plus 15 would be a 14. So I have a remainder, which is totally fine because our point here is not to check to see if this is a 0. We're trying to see the slant asymptote. In other words, what linear equation does this ratio get closer and closer to? So we have our f of x, and we took that division, and we divided the x cubed minus 1 over this x squared plus 3x plus 5. And what did we get for our quotient? Well, we got this quotient, so x minus 3, plus a remainder, right, 4x plus 14, over our divisor. Now, what I want to talk about is this remainder part. So I want to think about what this thing does. I want you to look at degrees. The degree in the numerator of this divisor is 1, and the degree in the denominator is 2. So I want you to think end behavior, like horizontal asymptote here. What would this approach as x approaches infinity? If we think about end behavior, if the degree is bigger in the bottom, what happens? Think about your horizontal asymptotes. It's 0, right? If the bottom of the fraction gets bigger and bigger and bigger, that means the value of the fraction gets closer and closer to 0. In other words, the further we go out on the graph, the smaller and smaller and smaller that remainder is going to get. It becomes what they call negligible, which is so tiny it doesn't even matter anymore. It's so small. And this is going to get closer and closer and closer then to f of x being equal to just this linear part of the equation, because this remainder is going to get so tiny. In other words, we get the equation y equals then x minus 3, and that is your slant asymptote. And I want you to be able to see that. So we're actually going to graph this on our calculator. So if you can go ahead and I'm going to, oopsies, clear these out here, my old equations. Let's go ahead and put in this first one in y1, if I can get it to go over there. Let's put in that original equation. So we've got our x cubed minus 1, and then in your denominator, we've got the x squared. And then is it minus, oh no, plus 3x, and then plus 5. So let's take a look at the original graph. So we get kind of an interesting looking thing here. Notice there's no vertical asymptotes happening, no breaks in the graph. And what might that mean if you don't have a vertical asymptote? Where do the vertical asymptotes come from? Whenever the denominator equals 0, right? So x squared plus 3x plus 5 equaling 0, those excluded values in the domain, there are no real answers to this. There's no numbers that make that true, which means there's no excluded values at all. There's no x-intercepts, right? Which means this graph doesn't cross the x-axis. So we don't have any excluded values, so we don't have any vertical asymptotes. If you're wondering why the graph looks that way, that's why. Let's go ahead and put in our slant asymptote. This is the cool part. Let's go ahead and put that in there. So x minus 3, and prepare to be amazed. Waha, there it is. Notice too that your graph does cross over the asymptote, which can happen. When we talk about approaching an asymptote, it's the end behavior, what it's doing at the ends of the graph. So it's totally fine down there in quadrant 3 if you see that it's crossing there. That happens. We can definitely cross over an asymptote. I know that seems a little bit non-traditional, but it definitely can happen. So that's where slant asymptotes come from doing that ratio. So let's try one more just to be sure we're okay. So we're going to do the whole kind of deal here. We're going to sketch it. We're going to look at all the different asymptotes this graph has and talk about what the picture would look like. So remember, the first thing that we always check for is your domain. So we're going to look for the domain of the function. Remember, your bottom can't be equal to 0 at all. So our domain for this one would be all reals, and the x can't be equal to 1. Now my question for you is 1 then a vertical asymptote, or is it a hole? So that is the question. So is this going to be a vertical asymptote, or is it a hole? So do you remember how we check for that? Well, we need to go back and simplify and see if we can divide out any common factors, because remember, the ones that are removable that we can divide out, those make the holes. So the holes are going to be the things that we can divide out. The asymptotes are the ones we're stuck with, the values that we still have left even after we simplify. So can you factor the numerator for me? Let's see, that would be x and x. What multiplies to -2 and adds to -1? Well, that would be a -2 and a +1. So take a look at that ratio. Can you simplify it? Well, no, they're not exactly the same. So what that means is I don't have a hole. I actually have a vertical asymptote then at x equals 1. I can't remove that discontinuity. So I'm going to have that vertical asymptote happening at that location. So x equals 1 is my vertical asymptote. All right, so let's talk horizontal for a second. Horizontal asymptotes. What do we check to find horizontal asymptotes? Well, we compare the degrees. We look at the end behavior. So the numerator is degree 2, the denominator is degree 1. So it's bigger in the top. What does that tell you? There are none. No horizontal asymptotes because the degree is bigger in the top. However, how much is a degree bigger in the top by? Exactly 1. So what does that mean? What kind of asymptote do we have? Slant. All right, so we have a slant asymptote for sure, because a degree is exactly 1 bigger. So how do we find a slant asymptote? We just divide. We see what that ratio gets closer and closer to. Now, thankfully, this is a degree 1, right, in the denominator, so we can actually use synthetic division. So we're dividing by 1. I have 1, negative 2. Let's go ahead and do our synthetic division here. So I'm going to bring down the 1, multiply, and then remember what we do here, add, right? So that would be 0, multiply would be 0, and we get a -2 remainder. And again, no worries about the remainder because again, we're looking at what the end behavior is. So the remainder is going to get closer and closer to 0. We're not looking for zeros here. We're trying to see what this quotient is. So we get a degree 1 equation. What would this represent then? Y equals 1x plus 0, and remember that -2 over, it's going to go to 0 anyway. We only want the linear part of this. So y equals x plus 0, or just y equals x is plenty, is our slant asymptote. So it's going to approach that identity line. So I'm going to go ahead and put that in on my graph. So 0, 0, 1, 1, 2, 2, that whole lovely thing. And so here's my slant asymptote, y equals x. Now that's really not enough to actually see the graph. So remember what we talked about yesterday. We tried to, or in the 2-6 day 2, we talked about how do we find some more points? What would be good things to do? And we talked about finding intercepts. So we're going to find the x-intercepts, and if or intercept, however many we have, and then we're going to find y-intercepts. So we're going to find those first. If we need more, we can do some additional points. But let's see if we can see where it crosses the axes here. All right, so how do we find an x-intercept? Well, you substitute in y equals 0 and you solve for x. So that means we're going to put in 0 and we're going to see if we can solve for x. So we have our x squared minus x minus 2 over our x minus 1. Now here's the deal. When you have something equal to 0 like that and it's a fraction, the very first thing I'd be doing would be multiplying both sides by this x minus 1. So what a lot of people realize is it doesn't really matter what the denominator is. 0 times anything is still going to be 0. What you're looking at is actually this numerator, right? That's what's going to matter. And I'm going to go ahead and write it in our factored form that we have already done because that's going to help me find my intercepts a little bit quicker here. So what would be my x values then? Looks like 2 and -1 are going to be my points. So x equals 2 and x equals -1 are my x-intercepts. How do I find a y-intercept? Same kind of idea, but instead of putting a 0 for y, I put in a 0 for x. And this is usually pretty easy for people to do because anything that has that x in it is going to be a 0. So I'm just going back to that original statement there. So 0 squared minus 0 minus 2 would be a -2, and 0 minus 1 would be a -1, so it looks like a +2. So it looks like it's crossing the y-axis at +2. And I think that should give us a pretty good shape to be able to tell. I think if people needed, oopsie daisies, this is off a little bit, sorry. It's going to give us enough of an indication, I think, of what that shape of the graph should look like. If we need some more additional points, you could definitely plug in some values like on your graphing calculator and solve. So let's see what this one looks like. So I'm going to go ahead and type that in here. So I'm going to do my original function here. So I've got x squared minus x minus 2, and then over x minus 1. And I'm going to go ahead and put my slant asymptote of y equals x in my y2. So there's my original function, and there's that slant asymptote. We can see that nice vertical asymptote happening at 1 as well. So it's kind of a cool different approach here when we look at exactly 1 greater in the numerator than the denominator. So those are called slant asymptotes. So you never can have a slant and a horizontal at the same time. It's one or the other, right? So that's the only way that we can look at those. So our essential question for today then, how can I find the slant asymptotes? We divide, right? Degree in the top is exactly 1 bigger than the bottom, so we divide that top by the bottom to find that slant equation.